Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this comprehensive series, we are going to dive deep into TCP troubleshooting using two of the most powerful packet analysis tools available on Linux and Unix systems, tcpdump and tshark. These tools are essential for any network engineer, system administrator, or security professional who needs to diagnose network issues at the packet level. TCP, or Transmission Control Protocol, is the backbone of reliable communication on the Internet. When things go wrong with TCP connections, whether it is slow performance, connection failures, or unexpected behavior, having the ability to capture and analyze packets becomes invaluable. Understanding what is happening at the wire level gives you insights that no other diagnostic method can provide. tcpdump is the classic command line packet analyzer that has been around for decades. It is lightweight, available on virtually every Unix-like system, and incredibly powerful for quick packet captures. tshark, on the other hand, is the command line version of Wireshark, offering more advanced protocol dissection and filtering capabilities. Throughout this presentation, we will explore both tools in detail, starting with the fundamentals of each tool and progressing to advanced troubleshooting techniques for real-world TCP problems. By the end of this series, you will have the skills to diagnose connection issues, identify performance bottlenecks, and analyze TCP behavior with confidence. The TCP three-way handshake. One of the most important sequences to understand when troubleshooting TCP is the three-way handshake. This is how every TCP connection begins, and problems during this phase are among the most common issues you will encounter. Let me explain the sequence diagram that illustrates this process. The diagram shows the interaction between a client and a server during connection establishment. The client initiates the connection by sending a SYN packet to the server. This SYN packet contains an initial sequence number, let us say X, which the client randomly generates. At this point, the client enters the SYN sent state, waiting for a response. When the server receives the SYN packet, it responds with a SYN acknowledgement packet. This packet serves two purposes. It acknowledges the client's SYN by setting the acknowledgement number to X plus 1, and it sends its own SYN with its own initial sequence number. Let us call it Y. The server now enters the SYN received state. Finally, the client completes the handshake by sending an ACK packet back to the server. This ACK acknowledges the server's sequence number by setting the acknowledgement number to Y plus 1. Once this packet is received, both sides enter the established state, and data transfer can begin. When troubleshooting connection problems, you will want to verify that all three packets of this handshake are present. Missing or delayed packets at any stage indicate specific types of problems. A missing SYN acknowledge might indicate the server is not listening on that port, firewall blocking, or the server being overloaded. A missing final acknowledge could indicate client-side issues or network problems on the return path. Being able to capture and identify these packets is fundamental to TCP troubleshooting. tcpdump basic command structure. Let us examine the basic command structure of tcpdump and understand the most commonly used options. Mastering these options will give you the foundation for effective packet capture. The first command shows the most fundamental usage. We start with sudo because tcpdump requires root privileges to put the interface into promiscuous mode. The -i option specifies which network interface to capture on, in this case eth0. This is often the first option you will use because you need to tell tcpdump where to listen. The second command adds the -c option, which limits the capture to a specific number of packets. Here we are capturing exactly 100 packets on the eth0 interface. This is useful when you want a quick sample without capturing indefinitely. The third command introduces the -w option, which writes the captured packets to a file instead of displaying them on screen. The filename capture.pcap uses the standard pcap extension. This is essential when you need to capture packets for later analysis or want to open them in Wireshark. The fourth command shows how to read a previously captured file using the -or option. Instead of capturing live traffic, tcpdump reads and displays packets from capture.pcap. You do not need root privileges for this operation since you are just reading a file. The fifth command demonstrates capturing on all interfaces simultaneously using the special interface name any. This is particularly useful on multi-home systems or when you are not sure which interface the traffic will arrive on. Each of these commands represents a fundamental operation you will perform regularly. The interface selection, packet count limiting, file writing, file reading, and multi-interface capture are building blocks for more complex capture scenarios. tcpdump Berkeley Packet Filters. The real power of tcpdump comes from its filtering capabilities using Berkeley Packet Filter syntax. BPF filters allow you to capture only the packets you are interested in, reducing noise and focusing your analysis. The first command demonstrates filtering by host. By specifying host followed by an IP address, tcpdump captures only packets where that IP appears as either the source or destination. This is your most common filter for isolating traffic to or from a specific system. The second command shows port filtering. The port 443 filter captures all traffic on HTTPS port 443, regardless of which host is involved. This is useful when you want to analyze all encrypted web traffic on the network. The third command combines multiple conditions using the AND operator. Here we filter for traffic that involves host 192.168.1.100 and uses port 22, effectively isolating SSH traffic to a specific server. The logical and requires both conditions to be true. The fourth command demonstrates directional filtering with source and destination. The filter source host 10.0.0.1 captures only packets originating from that IP address, ignoring packets destined for it. Similarly, destination host would capture only packets going to a specific destination. The fifth command filters by protocol. The TCP filter captures only TCP packets, excluding UDP, ICMP, and other protocols. You can also use UDP, ICMP, or specific protocol numbers. The sixth command shows network-based filtering using the net keyword with CIDR notation. This captures all traffic within the 192.168.0.0/16 network, which is useful for isolating traffic on a specific subnet. These BPF filters can be combined in complex expressions using AND, OR, and NOT operators, along with parentheses for grouping. Mastering BPF syntax is essential for efficient packet capture, as it allows you to capture precisely what you need while ignoring irrelevant traffic. Tshark Basic Command Structure. Let us examine the basic command structure of tshark and how it compares to tcpdump. While many concepts are similar, tshark has its own syntax and additional capabilities. The first command shows the basic capture syntax. Like tcpdump, we use the -i option to specify the interface. Here we are capturing on eth0 with tshark. The second command demonstrates capturing to a file. The -w option works the same as in tcpdump, writing packets to the specified file. tshark defaults to the pcap-ng format, which supports additional metadata compared to the older pcap format. The third command shows how to read a previously captured file using -r. This is identical to tcpdump's syntax, making it easy to switch between tools. The fourth command introduces the capture filter syntax. The -f option specifies a BPF capture filter, in this case filtering for TCP port 80 traffic. These are the same filters you would use with tcpdump. The fifth command shows the display filter syntax using $Y. Here we filter for HTTP traffic using Wireshark's display filter syntax. The key difference is that display filters like HTTP operate on dissected packets and use different syntax than BPF capture filters. The sixth command demonstrates limiting the capture to a specific number of packets using -c, just like in tcpdump. Here we capture exactly 50 packets. Understanding the distinction between -f for capture filters and $y for display filters is crucial. Capture filters using -f are efficient but limited to basic packet header matching. Display filters using $y are powerful and can match any protocol field, but they operate after packets are captured and dissected, so they cannot reduce the amount of data captured, only what is displayed. Tshark display filters for TCP. One of tshark's greatest strengths is its display filter capabilities. These filters allow you to match on virtually any field in any protocol that Wireshark can dissect. For TCP troubleshooting, this is incredibly powerful. The first filter shows how to match TCP packets with specific flags set. The filter tcp.flags.syn operator 1 matches packets where the syn flag is set. This is useful for finding connection initiation attempts. The second filter targets TCP reset packets using tcp.flags.reset operator 1. Seeing or ST packets often indicates connection problems, either normal connection termination or abnormal conditions like connection refused. The third filter combines multiple conditions. The filter tcp.flags.syn operator 1 and sign and tcp.flags.ack operator 0 matches pure syn packets, which are the first packet of a three-way handshake. This excludes syn-ack packets where both flags are set. The fourth filter introduces the tcp.analysis namespace, which contains fields generated by Wireshark's TCP analysis engine. The filter tcp.analysis.retransmission matches packets that Wireshark has identified as retransmissions. This is invaluable for identifying packet loss. The fifth filter targets TCP window updates using tcp.analysis.windowUpdate. These packets indicate changes in the receiver's advertised window and can help diagnose flow control issues. The sixth filter shows how to find zero window conditions with tcp.analysis.0_window. Zero window packets indicate the receiver's buffer is full and it cannot accept more data, which is a common cause of performance problems. These tcp.analysis filters leverage Wireshark's sophisticated TCP stream analysis, which tracks sequence numbers, identifies retransmissions, and detects various TCP anomalies automatically. This analysis runs after packet capture and provides insights that would be extremely difficult to identify manually. tshark field extraction with -t fields. One of tshark's most powerful features for analysis is the ability to extract specific fields from packets and output them in a structured format. This capability transforms tshark from a packet viewer into a data extraction tool that can feed into scripts, spreadsheets, and monitoring systems. The "T fields option tells tshark to output only the specified fields rather than the full packet decode. Combined with "e" options that specify which fields to extract, you can build precise data extraction commands. Looking at the first command, we use "T fields to enable field extraction mode. The "e" options that follow specify exactly which fields we want. Frame.time gives us the timestamp of each packet. IP.source provides the source IP address. IP.destination gives the destination IP address. TCP.source port shows the source port, and TCP.destination port shows the destination port. The result is a clean, tab-separated output of just these 5 fields for every packet. The second command adds the "E header operator Y option. This tells tshark to include a header row showing the field names, which makes the output self-documenting and easier to import into spreadsheet applications or data analysis tools. The third command demonstrates how to extract TCP-specific analysis fields. Here we are extracting tcp.stream, which identifies the conversation, tcp.sequence for sequence numbers, tcp.ack for acknowledgement numbers, and tcp.len for the payload length. This gives us the core data needed to analyze TCP stream behavior. The fourth command focuses on TCP analysis metrics. By extracting tcp.analysis.ack or TT, we get the round-trip time calculated from the time between sending data and receiving its acknowledgement. The tcp.analysis.retransmission field marks packets identified as retransmissions. This combination is invaluable for performance analysis. The fifth command shows how to combine field extraction with display filtering. The "Y" filter limits output to only retransmitted packets, and then we extract the stream number, sequence number, and timestamp. This produces a focused report of all retransmissions in the capture. Analyzing handshake success and failure. Once you have captured handshake packets, you need to analyze them to determine whether connections are succeeding or failing. Let me walk you through the diagnostic process. The diagram illustrates the decision tree for handshake analysis. We start at begin analysis, where we examine the captured packets. The first question is whether SYN packets are present. If no SYN packets exist, this indicates that either traffic is not reaching the capture point, the client is not attempting connections, or your filter is incorrect. If SYN packets are present, the next question is whether SYN acknowledge responses exist. When we see SYN packets but no SYN acknowledge responses, this points to several possibilities. The issue could be a server not listening condition where the destination port has no service. It could be a firewall blocking situation where a firewall is dropping the SYN packets silently. Or it could be routing issues where packets are reaching the server but responses cannot route back. When SYN acknowledge packets are present, we ask whether the final acknowledge exists. If we see SYN and SYN acknowledge but no final acknowledge, the problem is likely client-side issues. This could mean the client is not receiving the SYN acknowledge due to routing problems. A web application firewall on the client side is blocking inbound packets, or the client API has a bug or timeout issue. When all three packets of the handshake are present, we reach the connection success state. At this point, if there are still problems, the issue lies in the data transfer phase rather than connection establishment. This systematic approach helps you quickly narrow down where in the connection process things are failing, which directly points you toward the root cause. Diagnosing connection timeout. Connection timeouts are more challenging to diagnose than refused connections because they involve the absence of packets rather than the presence of specific packets. A timeout occurs when the client sends a SYN but never receives any response. The sequence diagram shows this scenario. The client sends a SYN packet to the server, but the packet either never arrives or the response never makes it back. After waiting, the client sends a SYN retry, attempting the connection again. This retry process continues, with the client sending additional SYN retry packets. Finally, after exhausting retries, the client reports a connection timeout to the application. The first command captures SYN packets without corresponding SYN ACK responses using tcpdump. The filter TCP flags equals 2 matches only pure SYN packets by checking for exactly the SYN flag with no other flags set. The value 2 represents the SYN flag bit position. We write to a file for later analysis. The second command uses tshark to identify SYN retransmissions specifically. The display filter tcp.flags.syn operator 1 and tcp.analysis.retransmission matches SYN packets that Wireshark's analysis has identified as retransmissions. Multiple SYN retransmissions for the same destination indicate the initial SYN is not getting through or the response is lost. The third command extracts details about retransmitted SYNs. We output the timestamp, source IP, destination IP, and destination port for each retransmitted SYN. This helps identify which connections are failing and when. The fourth command takes a different approach by looking for connections that have SYN packets but never reach the established state. The filter tcp.flags.syn equal operator 1 and not tcp.flags.ack equal operator 1 finds initial SYN packets. By examining these and correlating with the absence of SYN-ACK responses, you can identify timeout conditions. Connection timeouts typically indicate firewall issues silently dropping packets, routing problems preventing packets from reaching the destination, or the destination host being down or unreachable. TCP retransmission analysis. TCP retransmissions occur when the sender does not receive an acknowledgement within the expected time and must resend data. Identifying and analyzing retransmissions is critical for diagnosing packet loss and network quality issues. The diagram shows the retransmission mechanism. The sender transmits data with sequence number 1000 to the receiver. Under normal circumstances, the receiver sends back a CK2000 acknowledging receipt. The sender then transmits the next data segment with sequence number 2000, and the receiver acknowledges with a CK3000. However, when data segment 3000 is sent and the ACK is lost or delayed beyond the retransmission timeout, the sender does not receive confirmation. After waiting for the retransmission timeout period, the sender resends the same data with sequence 3000 as a retransmission. This time the receiver sends a CK4000 which successfully reaches the sender, and normal transmission resumes. The first tshark command identifies all retransmissions in a capture file. The display filter tcp.analysis.retransmission leverages Wireshark's built-in analysis that tracks sequence numbers and identifies when the same data is sent multiple times. The second command identifies fast retransmissions specifically. The filter tcp.analysis.fast_retransmission matches packets that were retransmitted in response to duplicate ACKs rather than timeout. Fast retransmissions indicate packet loss detected quickly through duplicate acknowledgements. The third command finds spurious retransmissions using tcp.analysis.spurious_retransmission. Spurious retransmissions occur when the original packet was actually received, but the sender retransmitted anyway, usually due to overly aggressive timeout settings. The fourth command extracts detailed retransmission data. We output the timestamp, stream number, sequence number, retransmission flag, and fast retransmission flag. This produces a comprehensive report that lets you analyze retransmission patterns across all connections. High retransmission rates indicate network problems such as congestion, lossy links, or misconfigured network equipment. Correlating retransmission timestamps with network events can help identify the root cause. Round-trip time analysis. Round-trip time, or RTT, is the time between sending data and receiving its acknowledgement. RTT analysis helps identify network latency issues and is critical for understanding TCP performance. The diagram shows how RTT is measured. The sender transmits data sequence 1000 at time T1 and records this timestamp. The data travels across the network to reach the receiver. After processing, the receiver sends back a CK2000 which travels across the network back to the sender, arriving at time T2. The RTT is calculated as T2 minus T1, representing the total round-trip delay. The first tshark command extracts RTT measurements from a capture. We use field extraction with "T" fields and request tcp.analysis.ack_RTT. This field contains the RTT calculated by Wireshark for each acknowledgement. The output shows the RTT in seconds for each packet that has this measurement. The second command adds context to RTT measurements by also extracting the timestamp and stream number. This lets you track RTT over time and identify which connections are experiencing high latency. The third command filters for high RTT values. The display filter tcp.analysis.ack_RTT greater than 0.1 finds packets with RTT exceeding 100 milliseconds. Adjust this threshold based on your network's normal baseline. The fourth command produces a comprehensive RTT report. We extract the timestamp, stream number, sequence number, and RTT for all packets with RTT measurements. By piping this through sort and analysis tools, you can calculate statistics like minimum, maximum, average, and percentile RTT values. The fifth command uses tshark's statistics capability with -zio, stat to generate interval-based statistics. While this shows packet counts, you can combine field extraction with command line tools to calculate RTT statistics over time intervals. Higher variable round-trip time indicates network congestion, routing inefficiencies, or geographic distance between endpoints. Sudden round-trip time increases often correlate with packet loss events as congestion builds. Understanding your baseline round-trip time helps you identify when network conditions degrade. Identifying TCP reset causes. TCP reset packets deserve special attention because they indicate abnormal connection termination. Understanding the various causes of RST packets helps you diagnose connection problems quickly. The diagram categorizes the common causes of TCP resets. The TCP reset causes branch into several distinct scenarios. Connection refused occurs when the destination port has no listening service. The operating system's TCP stack automatically sends RST in response to SYN packets on closed ports. Application crash happens when a process terminates unexpectedly while connections are open. The kernel sends RST packets to all connected peers because the receiving application is no longer there to handle the data. Firewall reset occurs when network security devices are configured to actively reject rather than silently drop connections. Some firewalls send RST packets to terminate blocked connections immediately rather than letting them time out. Connection timeout can trigger RST when idle connections exceed configured timeouts. Load balancers, firewalls, and NAT devices often terminate stale connections with resets. Invalid packet indicates RST sent in response to packets that do not match any known connection. This can happen with asymmetric routing, state table overflows, or protocol violations. Resource exhaustion causes RST when the system cannot allocate resources for new or existing connections. Memory pressure or connection limits can trigger this behavior. The first tshark command identifies RST packets by source. We filter for resets and extract the source IP, destination IP, and ports. Grouping resets by source helps identify whether resets originate from servers, clients, or network devices. The second command looks for RST packets that follow SYN packets, indicating connection refused. By capturing both SYN and RST packets and examining the sequence, you can confirm the refused connection pattern. The third command finds RST packets mid-connection. The filter tcp.flags.reset equals operator 1 and tcp.sequence greater than 1 finds resets with sequence numbers indicating they occurred during an established connection rather than during handshake. Correlating RST packets with their context helps determine the cause. RST immediately after SYN suggests no listener. RST after data transfer suggests application or firewall issues. Patterns of RSTs across many connections suggest systemic problems. TCP stream following and conversation analysis. When troubleshooting TCP issues, you often need to focus on a single conversation rather than all traffic in a capture. Both tcpdump and tshark provide mechanisms to follow individual TCP streams, which is essential for understanding what happened in a specific connection. A TCP stream is identified by the 4-tuple of source IP, source port, destination IP, and destination port. Wireshark and tshark assign each unique conversation a stream index number starting from 0, making it easy to reference specific connections. The diagram illustrates how multiple TCP streams coexist in a capture. Stream 0 represents a connection between client A and server on port 443. Stream 1 shows a different connection from client B to the same server, also on port 443. Stream 2 represents yet another connection from client A but to a different destination, server 2 on port 80. Each stream is completely independent, with its own sequence numbers, window sizes, and state. Understanding stream identification is crucial because TCP analysis fields like retransmissions, RTT measurements, and window tracking all operate within the context of a single stream. A retransmission in stream 0 has no relationship to packets in stream 1. When you filter by stream number, you isolate all packets belonging to that specific conversation. The first tshark command demonstrates basic stream filtering. The display filter tcp.stream equals operator 0 shows only packets belonging to stream 0. This isolates a single conversation for detailed analysis. The second command uses the follow feature to reconstruct the TCP stream content. The -z option with follow, TCP, ASCII, 0 tells tshark to follow stream 0 and display the payload in ASCII format. This is incredibly useful for seeing what data was actually exchanged. The third command extracts all unique stream numbers in a capture. By requesting just the tcp.stream field and piping through sort and unique, you get a list of all conversations in the capture file. This helps you understand the scope of the capture. The fourth command counts packets per stream. This quick analysis shows which streams have the most activity, helping you identify the busiest or potentially problematic conversations. TCP options analysis. TCP options extend the protocol's capabilities beyond the basic header fields. Understanding these options is important for troubleshooting because they affect connection behavior, performance, and compatibility. The diagram shows the most important TCP options and their purposes. Maximum segment size, or MSS, specifies the largest segment the sender can receive. This option is exchanged during the handshake and affects how data is segmented. Incorrect MSS values can cause fragmentation or performance issues. Window scale extends the 16-bit window size field to support larger windows. The scale factor is a power of 2 multiplier applied to the window value. This option is essential for high bandwidth, high latency connections where the standard 65,535-byte window would limit throughput. Selective acknowledgement, or SACK, allows the receiver to acknowledge non-contiguous blocks of data. Without SACK, a single lost packet forces retransmission of all subsequent data. With SACK, only the lost segments need retransmission, significantly improving recovery from packet loss. Timestamps serve two purposes. They enable precise RTT measurement independent of sequence number wraparound, and they provide protection against wrapped sequences, or PAWS, which helps detect old duplicate packets on high-speed connections. The first tshark command extracts TCP options during the handshake. We filter for SYN packets and output the MSS value, window scale factor, SACK permitted flag, and timestamp values. This shows what options each endpoint supports. The second command filters for packets where window scaling is present. The filter tcp.options.wscale checks for the window scale option. This helps verify that window scaling was negotiated successfully. The third command examines SACK blocks in acknowledgements. The display filter tcp.options.sack shows packets containing SACK information. The field tcp.options.sack_le extracts the left edge of SACK blocks, showing which byte ranges were received out of order. The fourth command analyzes timestamps. Extracting tcp.options.timestamp.tsval and tcp.options.timestamp.tsecr shows the timestamp value and echo reply, which can be used to calculate RTT and detect timing anomalies. Duplicate ACK analysis. Duplicate acknowledgements are a key indicator of packet loss or reordering in TCP. When a receiver gets an out-of-order packet, it immediately sends an ACK for the last in-order byte received. Multiple identical ACKs signal to the sender that something is missing. The sequence diagram shows how duplicate ACKs work. The sender transmits data segments with sequence numbers 1000, 2000, and 3000. However, the segment with sequence 2000 is lost and never reaches the receiver. When the receiver gets sequence 3000, it realizes 2000 is missing. Instead of acknowledging 3000, it sends a CK2000 again, indicating it still needs byte 2000. The sender continues sending data with sequence 40. Again, the receiver sends a duplicate ACK20 because it still has not received that segment. When the sender continues with data 50, the receiver sends yet another duplicate ACK20. This is now the third duplicate. 3 duplicate ACKs, meaning 4 total ACKs for the same sequence number, trigger TCP fast retransmit. The sender immediately retransmits the missing data with sequence 2000 without waiting for the retransmission timeout. Once the receiver gets this segment, it can acknowledge everything it has buffered, sending a CK6000. The first tshark command finds all duplicate ACKs. The display filter tcpdump_ACK matches packets that Wireshark has identified as duplicates based on sequence number analysis. The second command counts duplicate ACKs per stream. By extracting the stream number for each duplicate ACK and counting, you can identify which connections are experiencing the most loss. The third command shows the duplicate ACK number. The field tcpduplicate_ACK_num indicates which duplicate this is, where 1 is the first duplicate, 2 is the second, and so on. 3 or more duplicates typically trigger fast retransmit. The fourth command correlates duplicate ACKs with the data they are requesting. By examining the acknowledgement number in duplicate ACKs, you can identify exactly which sequence number is missing and cross-reference with the original transmission to understand the loss pattern. High duplicate ACK rates indicate network issues such as congestion, faulty equipment, or routing problems. Analyzing where in the capture duplicates cluster can help identify when problems occurred. TCP Keep Alive Analysis. TCP Keep Alives are probe packets sent on idle connections to verify the peer is still reachable. Understanding keep alive behavior is important for troubleshooting connections that unexpectedly terminate after periods of inactivity. The sequence diagram shows the keep alive mechanism. After the connection is established, both sides enter an idle period where no data is exchanged. After a configured timeout, typically 2 hours by default, the side with Keep Alives enabled sends a Keep Alive probe. This is a packet with no data and a sequence number 1 less than the next expected sequence. The peer responds with a Keep Alive ACK, confirming it is still alive and reachable. The connection remains open, and another idle period begins. This cycle continues as long as the connection remains idle. If the peer has crashed or become unreachable, the Keep Alive probe receives no response. After several probes without response, the connection is aborted and enters a connection dead state. This mechanism ensures dead connections are eventually cleaned up rather than persisting indefinitely. The first tshark command identifies Keep Alive probes. The display filter tcp.analysis.keepalive matches packets identified as Keep Alive probes based on their characteristics, specifically having sequence numbers that probe the connection state. The second command finds Keep Alive acknowledgements. The filter tcp.analysis.keepalive_ACK matches the responses to Keep Alive probes. The third command extracts Keep Alive timing. By outputting timestamps for Keep Alive events along with the stream number, you can analyze the Keep Alive interval and verify it matches expected configuration. The fourth command helps identify failed Keep Alives. We look for Keep Alive probes that were not followed by an acknowledgement. If you see multiple Keep Alive probes without responses, the peer may have become unreachable. Keep Alive related issues often arise when firewalls or NAT devices have shorter idle timeouts than the TCP Keep Alive interval. The stateful device closes its mapping before keep alives can maintain it, causing the connection to break. In such cases, reducing the keep alive interval or using application-level heartbeats can help. Combining tcpdump and tshark effectively. While tcpdump and tshark have overlapping capabilities, they each have strengths that make them better suited for different tasks. Understanding when to use each tool, and how to combine them, makes your troubleshooting more effective. The diagram illustrates a recommended workflow combining both tools. The process begins with tcpdump capture. You use tcpdump for the initial capture because it is lightweight, universally available, and excellent at efficiently capturing packets with BPF filters. tcpdump writes to a pcap file that can be analyzed later. The captured pcap file then becomes input for tshark analysis. Tshark excels at detailed protocol dissection, display filtering, and field extraction. You can run multiple tshark commands against the same capture file, exploring different aspects of the data. From tshark analysis, you can generate various outputs. Statistics provide summary information like packet counts, conversation lists, and protocol hierarchies. Filtered exports let you extract specific streams or packet types to smaller files. Field data gives you structured extraction of specific fields for further processing. These outputs can feed into further analysis. The spreadsheet path shows how field data can be analyzed in Excel or similar tools. The scripts path indicates programmatic analysis using shell scripts, Python, or other languages. The visualization path leads to tools that can graph the data. The first command shows a typical tcpdump capture command. We capture on eth0, write to a pcap file, and use a BPF filter for specific host and port. The -s0 ensures we capture complete packets rather than truncating them. The second command demonstrates initial tshark analysis. We generate a protocol hierarchy statistics report showing what protocols are present and their relative prevalence in the capture. The third command extracts conversation statistics. The -zip-conv TCP option produces a summary of all TCP conversations including packet counts, bytes transferred, and duration. The fourth command extracts specific fields for external analysis. We output stream numbers, timestamps, or TT values, and retransmission flags in a format suitable for importing into other tools. This combined workflow leverages the efficiency of tcpdump for capture and the analytical power of tshark for detailed examination. Performance baselining techniques. Effective troubleshooting requires knowing what normal looks like. Performance baselining establishes reference metrics that you can compare against when problems arise. Let me walk you through techniques for establishing TCP performance baselines. The diagram shows the key metrics to baseline and their relationships. Starting from TCP performance metrics, we branch into several categories. Latency metrics include TT measurements, which reflect the round-trip delay, and connection time, which measures how long the three-way handshake takes. Loss metrics cover retransmission rate, expressed as a percentage of packets that required retransmission, and duplicate ACK rate, which indicates how often receivers signal missing data. Throughput metrics include bytes per second measuring actual data transfer rate, and goodput measuring useful data excluding retransmissions and overhead. Flow control metrics track zero-window events counting how often receivers advertise zero window, and window size distribution showing the range of advertised window sizes. The first command extracts TT data for baseline analysis. We output TT values for all packets that have this measurement, then use command line tools to calculate statistics. Piping through awk, we can compute minimum, maximum, average, and other percentiles. The second command calculates retransmission rate. We count total packets and retransmitted packets separately, then compute the percentage. A healthy connection typically has retransmission rates well under 1%. Case study. Diagnosing slow connections. Let us work through a real-world case study of diagnosing slow TCP connections. This scenario is one of the most common issues you will encounter, and it demonstrates how to apply the techniques we have learned. The problem presents as users reporting slow application performance. The application connects to a backend service over TCP, but response times are unacceptable. Our task is to determine whether the issue is network-related and, if so, identify the specific cause. The diagnostic workflow diagram shows our approach. We start at the problem reported stage where users complain about slowness. The first step is to capture traffic between the client and server during a slow transaction. We use tcpdump with appropriate filters to minimize capture size while getting the relevant data. Next, we measure our TT using tshark to extract round-trip time measurements. We compare these against our baseline or expected values. If our TT is high, we have identified network latency as a contributing factor. We then check retransmissions to see if packet loss is occurring. High retransmission rates cause delays as the sender waits for timeouts and resends data. Even a few percent retransmission rate can significantly impact perceived performance. The next step is to analyze windows to see if flow control is limiting throughput. Zero window events or persistently small windows indicate the receiver cannot keep up with incoming data, throttling the sender. We also check application delays by examining the time between receiving a request and sending the response. Long gaps in the packet flow without TCP-level issues suggest the application itself is slow to process. Finally, we arrive at the root cause, which might be network latency, packet loss, receiver bottleneck, or application processing time. The specific findings guide the remediation effort. The commands shown demonstrate this workflow, from initial capture through our TT analysis, retransmission checking, and window examination. Application layer correlation. TCP troubleshooting often requires correlating network-level observations with application behavior. Understanding how to extract and match application data from packet captures bridges the gap between network and application teams. The diagram shows the relationship between TCP and application layers. The application layer at the top contains the application protocol such as HTTP, which carries application data like requests and responses. This rides on top of the TCP layer, which handles the TCP stream containing segments with sequence numbers and acknowledgements. Beneath that, the network layer handles IP packets with source and destination addresses. When troubleshooting, we often need to connect symptoms at one layer to causes at another. A slow HTTP response might be caused by TCP retransmissions. A failed API call might correlate with a TCP reset. Understanding these relationships is essential. The first command demonstrates HTTP extraction. Using tshark's HTTP dissector, we can extract request URIs, response codes, and response times. The http.time field shows how long the complete HTTP transaction took, which can be compared against TCP-level timing. The second command correlates HTTP with TCP stream numbers. By extracting both the TCP stream and HTTP fields, we can identify which TCP conversation carried a specific HTTP request, then analyze that stream in detail. The third command follows the TCP stream as ASCII to see the actual HTTP conversation. This shows the raw request and response headers and body, helping verify what the application actually sent and received. The fourth command identifies HTTP errors and their TCP context. We filter for non-200 HTTP responses and extract the stream number, allowing us to examine the TCP behavior around failed requests. The fifth command demonstrates extracting specific HTTP headers. By using fields like http.host and http.useragent, we can identify which clients and which virtual hosts are involved in specific transactions. This correlation capability extends beyond HTTP. Tshark supports dissectors for hundreds of protocols, allowing similar analysis for database connections, API calls, messaging protocols, and virtually any application layer communication. Remote capture techniques. Often the system you need to capture from is not your local workstation. Remote capture techniques allow you to collect packets from servers, network devices, or containers while analyzing them locally or on a dedicated analysis system. The diagram shows common remote capture scenarios. The remote server runs tcpdump and sends captured packets to your local workstation for analysis with Wireshark or tshark. The network device like a switch or router uses port mirroring, also called SPAN, to copy traffic to a capture server. The container environment uses special techniques to capture from container network namespaces. The first command demonstrates SSH-based remote capture. We SSH to the remote server and run tcpdump there, outputting to standard output with -w-. The data streams back through the SSH connection and pipes directly into the local Wireshark for real-time analysis. This is incredibly useful for live troubleshooting. The second command captures to a remote file, then copies it locally. We run tcpdump on the remote server, writing to a file there, then use SCP to copy the file to the local machine for analysis. This approach works better for large captures or unreliable connections. The third command shows capturing from a Docker container. We use docker exec to run tcpdump inside the container, piping the output locally. This captures traffic from the container's network namespace, seeing exactly what the containerized application sees. The fourth command captures from a Kubernetes pod. We use kubectl exec similarly to docker exec, running tcpdump inside the pod and streaming the capture locally. This is essential for troubleshooting in Kubernetes environments. The fifth command demonstrates capturing on a remote server and streaming to a local file. The SSH connection streams tcpdump output while we write it to a local pcap file for later analysis. Remote capture requires tcpdump or equivalent tools installed on the remote system and appropriate permissions. In locked-down environments, you may need to work with system administrators to enable capture capabilities or use alternative approaches like network device mirroring. Advanced tshark statistics. Tshark includes powerful built-in statistics capabilities that can summarize capture data without manual field extraction and processing. These statistics provide quick insights and can identify issues faster than examining individual packets. The diagram shows the categories of statistics available. Protocol statistics include protocol hierarchy showing the breakdown of protocols in the capture, and endpoint statistics listing all communicating hosts. Conversation statistics cover TCP conversations showing all connections, and UDP conversations for connectionless traffic. Expert analysis provides warnings and errors automatically detected by Wireshark's analysis engine, and packet lengths showing size distribution. I/O statistics include packets per interval, bytes per interval, and can be filtered to show specific traffic types over time. The first command generates a protocol hierarchy. The -zio, phs option produces a tree showing what percentage of traffic is each protocol. This quickly reveals what is in your capture and whether unexpected protocols are present. The second command shows TCP conversation statistics. The -z TCP option lists every TCP connection with packet counts, byte counts, and duration. This helps identify the busiest connections and potential outliers. The third command produces endpoint statistics. The -z endpoints IP option lists all IP addresses in the capture with their traffic volume, helping identify the most active hosts. The fourth command extracts expert information. The -z expert option shows all warnings, errors, and notes generated by Wireshark's expert analysis system. This automatically highlights potential problems like retransmissions, zero windows, and protocol errors. The fifth command generates I/O statistics over time. The -zio, stat, 1 option shows packet and byte counts per 1 second interval. Adding a filter lets you track specific traffic types, like showing only retransmissions per second. The sixth command shows packet length distribution. The -z tree option produces a histogram of packet sizes, which can reveal patterns like many small packets indicating chatty applications or many large packets indicating bulk transfers. These built-in statistics often answer questions faster than manual analysis, especially for initial triage of large capture files. Common pitfalls and how to avoid them. Before we conclude, let me share some common pitfalls in TCP troubleshooting and how to avoid them. Learning from these mistakes will make your troubleshooting more effective. The diagram organizes common pitfalls into categories. Capture mistakes include capturing on the wrong interface, which misses the traffic entirely, filters too restrictive, which excludes relevant packets, and no baseline capture, meaning you lack reference data for normal behavior. Analysis mistakes include ignoring one direction by analyzing only client to server or server to client, misinterpreting retransmissions by assuming all retransmissions indicate loss when some are spurious, and missing context by not considering what the application was doing during the capture. Tool mistakes include wrong filter syntax by confusing BPF capture filters with Wireshark display filters, missing timestamps by not enabling appropriate time display, and truncated packets by not capturing complete packets when payload analysis is needed. The first lesson addresses interface selection. Always verify which interface carries the traffic before capturing. Use IPadder or ifconfig to list interfaces, and tcpdump with "D" to show available capture interfaces. If unsure, start with "-i" to capture all interfaces. The second lesson concerns filter testing. Test complex filters before relying on them for critical captures. Run a short test capture and verify it contains expected traffic. Remember that BPF filter syntax differs from display filter syntax. The third lesson emphasizes bidirectional analysis. TCP conversations involve two directions. Analyzing only one direction can lead to incorrect conclusions. A retransmission in one direction might be caused by lost acknowledgements in the other direction. The fourth lesson highlights the importance of timestamps. Enable detailed timestamps when the timing of events matters. The "-tt" option in tcpdump shows timestamps with microsecond precision. In tshark, use frame.time delta to see time between packets. The fifth lesson warns against assuming packet loss. Not all retransmissions indicate real loss. Spurious retransmissions occur when acknowledgements are delayed. Out-of-order packets trigger duplicate ACKs. Look at the complete picture before concluding packet loss exists. Summary and best practices. We have covered a comprehensive set of techniques for TCP troubleshooting using tcpdump and tshark. Let me summarize the key points and best practices to take away from this presentation. The diagram presents the core best practices. Know your tools means understanding tcpdump for efficient capture and tshark for deep analysis, and using each where it excels. Capture strategically involves using appropriate filters, managing file sizes, and planning for the data you need. Analyze systematically means following a consistent workflow from handshake through data transfer to termination. Correlate layers means connecting network-level observations to application behavior for complete understanding. Baseline performance means establishing normal metrics so you can identify deviations. Automate repetitive tasks means scripting common analyses for consistency and efficiency. Document findings means recording what you found for communication and future reference. For tcpdump, remember that it excels at efficient capture with BPF filters operating in kernel space. Use "-n" to disable DNS resolution, "-s0 to capture complete packets, and "-w" to write to files for later analysis. Master BPF filter syntax for precise packet selection. For tshark, Leverage its protocol dissection capabilities and display filters for detailed analysis. Use "T" fields for structured data extraction, "Z" for built-in statistics, and "Y" for powerful display filtering. The TCP.analysis fields provide automatic detection of many TCP issues. For TCP specifically, understand the three-way handshake and verify it completes during connection troubleshooting. Know what retransmissions, duplicate ACKs, and window changes mean. Track round-trip time as a key performance indicator. Recognize RST packet patterns and their implications. The skills you have learned apply broadly across network troubleshooting scenarios. Whether debugging slow applications, investigating connection failures, or analyzing security incidents, the ability to capture and analyze packets provides insights available no other way. Thank you for your attendance. Please consider subscribing to the channel and liking this video.